our last speaker before coffee break. It's Nikolay Mikhaylovskiy with report States of LLM-generated text and face transition between them. Okay, thank you, Nikolay.
Thank you. As a kudos for previous speaker, I believe that's super cool work. He didn't really understand how important it is, but we'll talk about that because, like, yeah. So Ivan, like, super cool, but you don't understand what did you do. Actually, learning language from nonsense is a super cool task. I have been tasking linguists for years, and you kind of solve that. Okay, so we'll talk about more of a physics of artificial intelligence than of mathematics of that. Did I touch something wrong? Oh, here we go. Okay, so let's start with something super simple. Phases of solid matter. There are crystals. Crystals are simple elements, are placed regularly and are invariant with respect to shift. The variance of elements are limited. And long-range correlations, let me go this way. It clicks and there are no problems with that. It's just a little bit smaller, no problem. Then on the other side of the spectrum, there's gas-like stage when the locations of elements like atoms or molecules are random and they move also randomly. And the correlation decay exponentially. More interesting is a critical state. For water, critical point is like here, not to be messed with a tripole point. So here at the critical point, it's an equilibrium phase of two-phase system where both phases become the same. In this point, correlations decay according to a power law, not exponential law. Fluctuations grow indefinitely, and fractal structures and scale invariants appear at this point. So a phase transition was defined by Paul Ehrenfest back in 1933 as a discontinuity in free energy. Modern physics moved from free energy to different other properties of matter, but basically when we have a phase transition, we have a discontinuity in some important property of a matter. So let's move from this very basic physics to how human written texts are. Actually, human written text can be analyzed using distributional semantics. In a distributional semantics, you attach a vector to any item in the text. For example, Glove is a typical old school distribution semantic which attach a vector to a word. Modern distributional semantics attach a vector to a context, but that's not relevant to something where this. But anyway, if we have a sequence, one-dimensional sequence of vector, it's super easy to compute autocorrelations. And if we if we take like War and Peace in some language, in Russian, in English, French, whatever, build autocorrelations and plot in different coordinates, in logarithmic coordinates and in straight coordinates. We will see that in logarithm to logarithm coordinates, it looks like a straight line. That means that the autocorrelation decay behaves according to a power law. So, in human text, that depends on how the text is structured. If we shuffle randomly some text, it doesn't look like that at all. And if we take like long form novels and works in literature, philosophy, whatever, it's easier to see that autocorrelations behave according to a power law with some extensions that are specifically tied to some nuances in the data in autocorrelations at short distances, which become negative. So, but overall, for all human texts, the autocorrelations decay behaves according to the power law. And that doesn't depend much on language, although it does depend, but it's statistical errors. And that's obviously related to a multi-scale structure of human written texts. What is multi-scale structure? If we look at War and Peace, it consists of books. Books consist of parts, parts of chapters, chapters of paragraphs, then to sentences, to words, and to characters. So, human written texts have multi-scale structures. Autocorrelations in human written text decay according to power laws, and thus human written texts correspond to critical state. That's our previous work, and now let's look what happens with the texts that are generated by large language models. In first type of experiments, we take two small models, Quen and Phi, and generate medium-sized texts with different temperatures. And it's at low temperatures, large language models are well known to degenerate into repeated going on and on a similar sentences. And if we plot other correlations, we see clear periodic structures. We take fast Fourier transform and see a typical structure that relates to periodic structure. At high temperatures, like close to 3, the large language models generate gibberish, almost random. And in this case, the autocorrelations are also random, but fast Fourier transform consists mostly of one first mode at 0 and then a little bit of noise. And if we take a fast Fourier transform, drop mode at 0, and plot that against temperature, we see that around temperature equal to 1, we have a kind of phase transition from ordered state to unordered state. That relates to shift of power from 0 mode to periodic mode. But do we have a critical state somewhere? It's not clear, actually. If we compute autocorrelations at temperatures close to 1, large language models generate something that looks like human text. But if we go on and on and on, it also becomes strange. If we зависло. Не зависло. If we plot these autocorrelations this way and that, there are some that looks good and there are some that looks bad, so this apparatus doesn't help. Let's look at different kind of distributions over the texts. There are two well-known linguistics statistical laws. Zipf's law, that's a simple and well-known dependency between the frequency rand of work and its frequency in natural corpus. It's like frequency is 1 by R. Actually, not discovered first by Zipf, but it happens. And Heap's law also describes the variety of new words over the length of the documents, also not discovered by Heaps, actually discovered by Herden, but doesn't matter. And we use a variety of large language models to generate long-form texts at different temperatures. What we observe that Heap's law doesn't work at all for large language models. And the variety of tokens generated doesn't even approximately, even for simple cases, doesn't look like a straight line. But we can look at a similar, very similar indicator. The ratio of the tokens first appearing in the first and the second part of the text. So we just cut the text in halves and look how much tokens first appeared, how many tokens have appeared in the first part and in the second part. And if we draw this diagram versus temperature, we see that this diagram has a pronounced maximum at around 1. That's promising. One model that doesn't look quite like that is Mistral. It's like something different, but overall probably also looks like that. Actually, Mistral is not the only mixture of experts. Think here, because Granite is also a mixture of expert models. So it's not that, like, we can't attribute that to Mistral being a mixture of experts. Let's look at, it's kind of promising, but doesn't explain anything. So let's look at zipflow for LLM-generated texts. Zipflow is like, here's zipflow for critic of pure reason in German. It's like, it's not like a exactly straight line, but it's enough of a straight line to allow us talking about power law decay. If we look at whatever generated by large language models, it doesn't look like that at all for most cases. But at temperatures close to 1, it may look like pretty much like a straight line in logarithmic coordinates for some range. At high temperatures, it again starts to be like very messy. But what can we do? We can like do least squares fitting and compute a mean absolute percentage error. And if we plot this kind of error versus the temperature, we can see a pretty pronounced minimum. That means that at temperatures close to 1, slightly different for different models, like going from 1 to 1.1 to 1.2, we see that at these temperatures, the text generated by large language models behave according to a power law. And that's combined with previous evidence, we can tell that at temperatures close to 1, the text generated by large language models do more or less confirm to a critical state. So, in a nutshell, there are three phases in LLM-generated text, depending on generation temperature. In gas-like state, long-range order doesn't exist independently from large temperature and a large language model. At low temperature, there's a crystal-like state, and a phase transition happens at temperatures around 1 independently from large language models. And at temperatures around 1, depending on large language model, generated text exhibit a state close to what we can describe as a critical state. That's it.
Okay. Thank you, Nikolay, for your excited report. I would like to notice that it's one of the powerful paper which will be selected from our conference, and I'm very happy that Nikolay participate on this conference. I hope he will be permanent member of our conference in future. And if you have some short questions before break, you can ask Nikolay, and we go on the break. Who have a question? Oh, okay. If you please, Andrei Vitalyevich. Give me, take.
Very interesting results. And one question: can we use your results to distinguish the text from LLM and from human?
Practically not. Because what we study is long-range correlations, and that all works on reasonably large texts. So I believe the practical value of what we are doing is more in understanding how does large language models work, rather than solving this practical task, which is important, of course, and everybody checking somebody's text, of course, wants to know how much of that is generated by large language models. But there are more practical ways, and there's research including, by the way, Russian guys at Huawei Research Center, and they kind of have the state-of-the-art in that.
If you have 10,000 characters, does it work?
If we have 10,000 words, that definitely works.
Characters.
Characters, probably not.
Okay, thank you. Additional congrats. Okay, and we are going to the coffee break.